In this problem, we're given the mass of the iron and the oxygen in the compound, and we're asked to determine the empirical formula. We know that an empirical formula gives us the ratio of one element to another in a compound, but it's not the ratio of the masses, it's the ratio of the number of atoms. Since the counting unit we use in chemistry is the mole, our first step is to express the amount of iron and oxygen in moles rather than grams. To determine the number of moles of iron, we need to use the molar mass. Molar mass for iron is 55.85 grams per mole. This gives us 0.0226 moles of iron. Notice that the mass of oxygen is not given in the problem. The mass of the compound is given as 1.80 grams, and the mass of the iron is 1.26 grams. Therefore, we have to subtract and determine that the mass of the oxygen is 0.54 grams. Of course, we need moles again, so we use the molar mass of oxygen, 16.00 grams per mole, to determine that there are 0.0338 moles of oxygen. To determine the ratio of number of moles of one element to the other, we divide each of these numbers by the smallest of these numbers, which in this case is 0.0226 moles. When we divide 0.0226 moles by itself, we get the number 1. When we divide 0.0338 moles by 0.0226 moles, we get the number 1.5. Since the subscripts in an empirical formula need to be whole numbers, we can't leave the ratio as 1 to 1.5. To make this a whole number ratio, we'll multiply all of the numbers by 2. This gives us a ratio of 2 for iron and 3 for oxygen. We're multiplying by 2 because the 0.5 is the decimal form of the fraction 1/2. 2 moles of iron and 3 moles of oxygen mean that our empirical formula is Fe2O3. In this problem, we're asked to determine the empirical formula from mass percent data. Because the empirical formula doesn't depend on how much compound you have, we can assume we have any amount we want. To make the math the easiest, let's just assume we have 100 grams. This means that for carbon, we would have 40.9 grams. And for hydrogen, we would have 4.48 grams. And of course, we can see that they didn't give us the percentage for oxygen, so we need to get the percentage for oxygen by subtracting the percentage of carbon and hydrogen from 100%. This gives us a mass for oxygen of 54.6 grams. Again, we need amounts in moles, not in grams, so we're going to use the molar mass, which is 12.01 grams per mole for carbon, which gives us 3.41 moles of carbon. We use the molar mass for hydrogen, 1.008 grams per mole, which gives us 4.44 moles of hydrogen. And we use the molar mass of oxygen, 16.00 grams per mole, which gives us 3.41 moles of oxygen. We divide each of these numbers by the smallest number of the three, which is 3.41 moles. And when we do this, it gives us 1 mole of carbon, 1.3 moles of hydrogen, and 1 mole of oxygen. Because the subscripts in an empirical formula have to be whole numbers, we'll multiply each of these numbers by 3. This gives us 3 moles of carbon, 4 moles of hydrogen, and 3 moles of oxygen. We multiplied by 3 because 0.3 is the decimal form of 1/3. Now we know that our empirical formula can be given as C3H4O3. In this problem, we're given the molar mass of the compound, and we're also given its empirical formula. What we're asked for is its molecular formula. To figure this out, we need to determine the molar mass of the empirical formula. We can see that there are 4 carbons, that's 48 grams per mole. There are 5 hydrogens, that's 5. 2 nitrogens is 28. 1 oxygen is 16, for a total of 97 grams per mole. Since my answer is going to be a chemical formula, I don't have to be concerned with the decimal places in the molar masses. Now, to determine the molecular formula, I take the molecular formula molar mass, which was given in the problem, and I divide it by the empirical formula molar mass, which we just added up. Plugging these numbers in, we have 194.2 grams per mole divided by 97 grams per mole, which gives us the number 2. This means that we have to multiply all of the subscripts in our empirical formula by the number 2, giving us a molecular formula of C8H10N4O2. In this problem, we're asked again for the molecular formula. We know we can get the molecular formula from the empirical formula and the molar mass. We're given the molar mass, but this time we're not given the empirical formula. We're given the percent composition information, and we have to determine the empirical formula from that. Again, assuming we have 100 grams of our compound, this gives us 40 grams of carbon, and carbon has a molar mass of 12.01 grams per mole, giving us 3.33 moles of carbon. Hydrogen has a mass of 6.71 grams and a molar mass of 1.008 grams per mole, giving us 6.66 moles of hydrogen. Again, we see that the percentage of oxygen is not given. We have to subtract the percentage of the hydrogen and the percentage of the carbon from 100%. This gives us 53.3% oxygen, which becomes 53.3 grams. And of course, the molar mass for oxygen is 16 grams per mole, giving us 3.33 moles of oxygen. Dividing by the smallest of these numbers, which is 3.33, we get 1 mole of carbon, also 1 mole of oxygen, and 2 moles of hydrogen. These are all whole numbers, so this ratio is good, and it turns out then that our empirical formula is CH2O. Now that we have the empirical formula, we can determine the molecular formula by dividing the molecular formula molar mass by the empirical formula molar mass. The molecular formula molar mass is given in the problem, and we can add up the molar mass of the empirical formula. 1 carbon is 12 grams per mole, 2 hydrogens is 2 grams per mole, 1 oxygen is 16 grams per mole, giving us a total of 30 grams per mole. Plugging these numbers in, we have 90 grams per mole divided by 30 grams per mole, which is equal to 3. This means that all of the subscripts in the empirical formula need to be multiplied by 3 to get the molecular formula, giving us a molecular formula of C3H6O3.